properties of power spectral density function. Here we have considered that Sxx of omega is power spectral density function of x of t, which is which is White's and stationary random process. Okay, so x of omega is power spectral density function of x of t, where x of t is White's and stationary random process. Okay, now we'll discuss the properties of power spectral density function, the statements. So the first property is that Sxx of omega is always greater than or equal to 0. This is our first property. That is power spectral density function is non-negative. Power spectral density function is non-negative. This is our first property. Then the second property is that the power spectral density function at omega is equal to 0. At omega is equal to 0 gives the area under, it gives us the area under the autocorrelation function. Okay. So the power spectral density at omega is equal to 0 gives the area under autocorrelation function Rxx of phi. Okay. So the third property is that the power spectral density function of real random process. So if x of t is real random process, then what is Sxx of omega will be equal to Sxx of minus omega. So if x of t is a real random process, what is power spectral density function is even. It is even. Okay. So that is our third property. Then the fourth property is that Sxx of omega is always a real function. It is always a real function. This is our fourth property. Then fifth property is that if Sxx of omega is power spectral density function of White's and stationary random process x of t, White's and stationary random process x of t, then okay, so it is given like this: 1 by 2 pi integral minus infinity to plus infinity Sxx of omega d omega is equal to the time average of expected value of x square of t. Okay, so the time average of expected value of x square of t is nothing but Rxx of 0. That is the time average of mean square value of White's and stationary random process equals the area under the curve of power spectral density. Okay, so what is this? The time average of mean square value. Okay, mean square value is equal to what? It is equal to the area under the curve of power spectral density function. That is our fifth property. And sixth property is that if x of t is White's and stationary random process, okay, then with the PSD of this is given as Sxx of omega. Okay, then the PSD of derivative of x of t is omega square times of PSD of x of t. That is Sx dot x dot of omega is equal to what? Omega square Sxx of omega. Here we will be using the property of Fourier transform. So we know that what is the property of Fourier transform? The derivative of x of t. Fourier transform is what? J omega minus j omega x of omega. We'll be using this property of Fourier transform to prove this. Okay. So that the PSD of derivative of x of t is equal to what? Omega square of PSD of x of t. That is omega square of s x of omega. This is our sixth property. And the seventh property is that the power spectral density function and time average of autocorrelation function form a Fourier transform pair. It will form Fourier transform pair. Okay. So what is that? It is given like this: s x of omega is equal to integral minus infinity plus infinity r x of tau e power minus j omega tau b tau. Okay. Similarly, r x of tau is equal to 1 by 2 pi integral minus infinity to plus infinity s x of omega e power j omega tau d omega. So these two will form Fourier transform pair. So here we will be discussing two nodes. Node 1 here is if x of t is wide sense stationary random process. If x of t is wide sense stationary random process, then what is r x of tau will be the inverse Fourier transform of s x of omega. This will form Fourier transform pair. So this relation is called Wiener-Khinchin relation. This relation is called Wiener-Khinchin relation. Okay, this is very important. So the proof of this property will give you, the proof of this property gives us the Wiener-Khinchin relation. This is our node 1. And here we also will be discussing node 2. Okay, so from the node 2, what is that we will be discussing here? Once we know PSD, so if you know power spectral density function, we can obtain what is that? The autocorrelation function for wide sense stationary random process. If x of t is what? Wide sense stationary random process, PSD gives the complete information about autocorrelation function. Okay. So if x of t is not wide sense stationary, is non-stationary. If it is non-stationary, in that case, the PSD gives us the time average. It gives us the time average of, okay, average of autocorrelation function. Okay. So when we have time average, the time average of autocorrelation function we will be having for non-stationary random process. Okay. So the PSD gives the time average of autocorrelation function if x of t is non-stationary. If x of t is stationary, in that case, PSD gives us the complete information of autocorrelation. What PSD gives? PSD gives the autocorrelation function. Okay. So whereas if x of t is non-stationary, PSD gives the time average of autocorrelation function. So in the case of non-stationary random process, we will be discussing time average. In the case of stationary random process, we will be discussing the direct autocorrelation function.